So we're going to continue on with question 3, which is bend, don't break just yet, yield instead. So the stress strain curves, so this problem again is going to deal with essentially that second regime in our stress strain curve, so plasticity, so strengthening mechanisms, and we're going to get into all of that right now. So let's read the problem. So it says the stress strain curves below are all from the same material, but they all have been processed differently. This material is able to form alloys fairly easily and can incorporate solute into the crystal structure as well. Additionally, the material can nucleate precipitate particles as well. So there's some important phrases here in this problem statement. So all these stress strain curves are from the same material, processed differently. So we could form alloys and incorporate solute. So additionally, this material can nucleate precipitate particles as well. So it's already kind of starting to hint to you about the strengthening mechanism. So what was our first strengthening mechanism? It was work hardening. We know that the change in the yield stress is proportional to the dislocation density, the 1/2. We also have solute strengthening. So again, forming alloys, incorporating solute. We saw that the change in the yield stress is proportional to your concentration of solute, C-sol, to the 1/2. We also had our Hall-Petch, our grain size, ETCH, our grain size strengthening, so grain size. Yeah, erase that right here. So grain size. And we saw that the change in the yield stress was equivalent or was proportional to dg to the -1. And this holds up until basic grain size of approximately 10 nanometers. After that, it's no longer smaller grain sizes. It does not hold. And then finally, we had basically precipitate. And we had that graph of basically the bowing or cutting. So precipitate particle strengthening, we had kind of this graph here. We had a radius, sigma y. So at the certain critical radius, RC or RC, for example, we're going to cut here and then bow on this other side here. So it kind of looks like this, and then it decreases like that. So those are our 4 strengthening mechanisms. So this statement here, nucleating precipitate particles, that hints to number 4. Processed differently, this could relate to basically 1 or 3. And then incorporating solute forming alloys, that is directly to the second mechanism. But so again, that's where you can kind of start to read and get to where these problems are heading. So first problem says label the following. Actually, we can also we'll get to that a little bit later. Label the following values on the graph and give me quantitative values as well with units. So it's first asking for what is the ultimate tensile strength of D. So the ultimate tensile strength of D is going to be about right here. So that is my sigma UTS. It is also my stress at fraction. Again, these materials are fracturing essentially at this point. So I'm going to say that ultimate tensile strength of D is just going to be approximately, I'm going to say it's like 25 MPa. Again, not, I won't be too, harsh on that. Remember, it's about halfway there. 25, 26, 20, it doesn't really matter. What is the strain at failure of B? So the strain at failure is right here. You can scroll down. So that strain at failure, just on F of B, that's about 0.2, I'm going to say. And finally, what is the Young's modulus of A? So here, I'm going to say we lose, see right here, we start to lose, basically, we start to lose our, linearity. So I'm going to scroll down here. So that is, so I'm going to say this is like about, 37 MPa. And then we want to look at the strain value here. So I'm going to say this is about, let's say this is 0.02 strain. So here in this regime, it's linear. We produce these curves with a uniaxial tensile test, so I could use Hooke's law. So Hooke's law is just this, Young's modulus times your strain value. So my Young's modulus is going to be stress over strain, which is equal to 37 times 10 to the 6 pascals divided by my strain value, which is 0.02, and you can kind of check the math on this one. Yeah, so that's it for A. Again, pretty simple, straightforward question. Just kind of making sure that you all know how to interpret that stress strain curve. So excellent. So now let's see what's happening on the next page. Also, we need the yield stress of C. So let's go back up. What is the yield stress of C? I'm going to say again, about right here. So maybe again about, this is my deviating from linearity, sigma y of C. I'm going to say it's about 25 MPa again. Yep. So now let's go on to B. So what could be going on with each sample to explain the differences in yield strength? Each sample actually has a different strengthening mechanism occurring. Describe what strengthening mechanism could occur, how the yield stress scales with each mechanism, and give a rationale for the strengthening mechanisms occurring and why it leads to higher or lower yield strength. Oh, that is a lot there. So let's start off with describing what is the yield strength of all these different materials. So the yield strength of these materials basically scales here, right? Because this is my yield strength of A, this is approximately my yield strength of B, and C, and then, D. So going back here, let's kind of write that yield stress of, go back here, yield stress of A is greater than the yield stress of B, which is greater than the yield stress of C, which is greater than the yield stress of D. So that's kind of our ranking here in terms of the yield stress, and that's just given from these curves. So we already listed our 4 strengthening mechanisms, and we know how they scale and what parameter they kind of scale appropriately. So we've already answered essentially this question here. So describe what strengthening mechanism could occur and how the yield stress scales with each mechanism. So we've got that answer. So, but we're asked, okay, if each of them, we have 4 materials, we have those 4 strengthening mechanisms. What could possibly lead to kind of these different, basically scaling phenomena, or what's going to, kind of push our yield strength up the most? So let's think about our 4 strengthening mechanisms. So I have my work hardening. I have, and that's going to be sigma y proportional to dissipation density squared. I could do my solute strengthening, sigma y proportional to C sol to the half. I have my grain size, Eg. So sigma y scales as Eg to the -1, and then I have my precipitate strengthening. So which one of these parameters? So all these values are kind of changing with a certain parameter. We'll get to precipitate in a bit. But again, we want to see how much, so if these are all the same material and all we're doing is processing, so what can push our yield strength the largest? So let's think about C sol. What is our kind of rule for forming an alloy? Well, really, our concentration of solute can really only be, C sol the maximum C sol and still be an alloy is approximately like 10 to 15%. So that's not a lot of kind of leeway, right, in terms of how we can increase our yield stress. So let's kind of go back and think about this now for a second. We'll keep that in mind. What about 1? Well, it scales with the dislocation density. We know that the dislocation density can vary tremendously, right? So we saw that for a highly annealed material, so a material that's been left basically in a furnace for long times at large temperatures, we can increase, or we can decrease the yield strength dramatically, and you'll see that the dislocation density can change by orders and orders of magnitude. So let's take a peek at that right now here. So we know that our yield strength, or basically that can vary quite dramatically. So for a highly cold work material, so our dislocation density for cold work material, it could be as high as 10 to the 14th dislocations per meter squared. For an annealed material, again, again, putting it at high temperatures, so high T, high temperatures for long times, you could basically diffuse out those dislocations. Your dislocation density can drop 7 orders of magnitude, 10 to the 7th dislocations per meter squared. So you're going to have a huge leeway here to kind of really dramatically push and change your dislocation density. So we're going to be able to change our yield strength considerably with our work hardening phenomenon. Additionally, for your grain size, you can shift this. Grains could be hundreds of micrometers or even larger, 100 micrometer grain size. But now you can even So 100 micrometers can be 1 grain size, but we would shrink it down. Again, this Hall-Petch, we could go down 100 micrometers to 10 nanometers. Orders of magnitude changes. So to me, I would rank, I think sigma A is our largest yield strength. So the reason why it's the largest yield strength is because this parameter, work hardening, can allow us to change our yield strength the most of all these different kind of mechanisms that we've been talking about. So I'd say that what could be happening, again, it's all depending on your justification. And again, this is kind of a thought experiment. It's just looking to make sure that you know kind of theoretically what's happening with these materials. I would say that material A is going to be work hardening, 1. Material B will be 3. The solute is last, and then my precipitate hardening could be my third, basically this kind of third one here. So 4 could be here. So that's what could be happening with these materials. So again, you could switch the order. Generally, I would think that the solute strengthening would be the least effective, and then again, the work hardening. You could switch work hardening and DG. Again, it's all about just kind of talking through this example and describing. I'm more looking for the scaling behavior here. That's the most important kind of parameter that we could kind of talk about here. So C, I really like this question. This has a definite answer. So the mechanism is precipitate strengthening. Will dislocations prefer to cut or bow around large particles? Well, we've already kind of, again, answered this by drawing that graph. So function of radius, there's some critical radius here, RC, and we get on this region of RC. So for small particles, what do we want to do? We want to, for small particle sizes, are we going to bow or are we going to cut? Well, small particle sizes, we're going to cut. Why do we want to cut for small particle sizes? 1, because if I have a small particle and I cut through it with my dislocation line, I'm not going to create as much surface area. That's kind of the deficiency, or kind of the energy penalty to pay for cutting your particle. So you don't want to kind of cut because it creates surface area. But for small particles, we don't create that much surface area. For bowing, if we have small particles, we're going to have to kind of basically kind of put our dislocation line in tension and wrap our dislocation line around that particle. That is going to create high curvature. So high curvature for small particles, that makes it energetically unfavorable to bow for small particle sizes. But as our particle size increases past this critical kind of value here, we are going to bow in this section. Why? Because as our particle gets larger and larger and larger, we're creating more and more surface area. That is not energetically favorable. So you get a curve that looks something kind of like this. So will dislocations prefer to cut or bow around large particles? We want to bow around large particles. We want to cut small particles. How will the critical radius for cutting versus bowing change if I drastically decrease the fraction of precipitate particles? So this is kind of like the inverse problem in our lecture. So we said that if I have 2 scenarios here, if I have particles that are all approximately the same size, but I have scenario 1, so I have a ton of particles in here, 1, and then 2, if I have kind of lots of particles in here, or a few particles in here, which is going to have the larger critical radius. Oh, if I'm in scenario 1, I have to, in terms of cutting, I'm creating way more surface area because there's more particles in here. So if I decide to cut, there's a lot of surface area being created when compared to the state 2. So if I decrease, it is going to be very energetically unfavorable to cut here. So your critical radius is going to shrink even further. You're going to need smaller and smaller particle sizes because you're creating more and more surface area. So for scenario 1, your RC, my critical radius, is going to be, for 1, is going to be much smaller than the critical radius for scenario 2. So if I drastically decrease my number of particle sizes, that critical radius is going to shift over here. It's going to increase because, again, I'm not creating as much surface area, so that's the energy penalty for cutting. That's it. It's just the inverse problem from that from the video where we kind of talked about strengthening mechanisms and kind of this issue of where does that critical radius shift depending on the fraction of particles, or precipitate particles. Excellent. So now to our last problem. One of my undergraduates looked at these curves and claimed the only difference was due to the grain size of each material. So they went on to investigate different mechanisms of creep at high temperatures and stresses. They forgot to fill out our regions. So we want to label all the regions, determine which corresponds to which stress strain curve, and then assuming the only processing difference is grain size. So let's go back and look at our deformation mechanism maps, which are right here. So unlabeled, we need to fill out kind of everything. So let's go ahead and get started. So again, just to kind of remind yourself, we know that sigma y of A is greater than sigma y of B is greater than sigma y of C is greater than sigma y of D. So now we claim, let's just make sure that that's actually the case. Yep, still true. So we're saying here the only strengthening mechanism at work is this one. So sigma y is proportional to dg to the minus 1. So we can rank grain sizes in our material. So we know that also that dg of A is less than dg of B is less than dg of C is less than dg of B. So we know our grain size in our material. So why is grain size important? Well, we're working with deformation mechanism maps. So we know that we're going to have our typical creep equation, our generic one right here, E prime for creep. So creep rate is going to be equal to Kc times sigma to the x power, dg to the y power, and we're going to have our d naught exponential minus qc over kt. Where, again, our table that we're going to work with Nabarro-Herring, Coble creep, and our dislocation law or power law creep. So we'll write this out again. It's in the notes. So mech, our q, our x, and our y values. All right, here. So for Nabarro-Herring, NH, Q is that's our lattice or our kind of volumetric contribution. X is 1, Y is -2 here. For our Coble creep, we have grain boundary diffusion. So again, this will dominate at very low temperatures because we know that our activation energy for GB is less than activation energy for L. The problem is there's much more volume, especially at large grain sizes. So we can only, in Nabarro-Herring or in Coble creep, we can only diffuse along these pathways. So for large grain sizes, the bulk diffusion in your grains here is going to dominate the mechanism. But as your grain size decreases, you're going to have a lot more pathways, and so that might make a contribution afterwards. X is 1, and then Y is 3. And then finally, our power law creep, it will be bulk again, and this dominates at 4 to 6, so high stresses. And 0. That's it. So let's now think, and actually let's notice a couple of things in this graph. So do you agree, why is this dashed line always at 10 to the minus 1? Well, we know this is our theoretical theory yield stress. I'm going to label this as TYS. So our theoretical yield stress is always going to be at that dashed line. We've kind of looked back to that in the notes. So theoretical yield stress always in here. TYS, TYS. So we're already starting to kind of label it. What's kind of the next? What does this line kind of denote here? This line here tells you where your material is just moving by dislocation glide. Dislocation glide. Because again, above here, you're yielding, the material is just beyond the yield, it's yielding, and your stress is beyond the theoretical yield stress above that dashed line. Below it, it's just yielding by your typical kind of dislocations moving around here. So I'm going to label this DG, dislocation glide. That's that section. G, DG, and DG. So now let's label kind of some sections here. So let's look at one. These have kind of our typical 3 curves. So what's going to be the topmost section after dislocation glide? Well, it's going to be our power law creep, right? Because that region, this kind of mechanism dominates at high stresses, so high Y values. So the topmost section is always going to be your power law creep. PLC, PLC, and PLC. What is going to be your rightmost, so below power law creep and to the rightmost, what's going to be that mechanism? That's going to be Nabarro-Herring, right? Because this QL, it's only going to dominate once we get at high temperatures, because this activation energy is larger than this activation energy here. So it's only going to dominate at high temperatures when we can get really this full contribution from all of the volume that's kind of occurring inside of these grains here. So this is NH, H, NH, H. What's going to be our final, the leftmost kind of region in here? Again, at lower temperatures, our cobalt creep is going to dominate. Why? Because again, this activation energy is lower than QL. So it is going to be able to kind of move and diffuse along these grain boundaries, again, at a lower temperature because that activation energy is lower when compared to your bulk diffusion mechanism. So I'm going to call this CC. Yeah, you know what I've done. So do the CC, CC, CC. So is there a cobalt creep in this top left? No, there's only two regions. So we'll talk about what that means in a second, how we could correlate that to kind of what our answers are. And then finally, in this region, low stresses, low temperatures, we're just elastic. We're below the dislocation glide. I'm just write this as E is elastic. So now it's time to label our curve. So what do you think is going to be A? So A has the smallest grain size, right? Because let me scroll up a little bit. A has our smallest grain size. So which region should be the largest? Which region scales with grain size the most? It's this one right here, right? So this region scales with grain size the most. It should be the largest. So I know just from looking at the size of this cobalt creep region, this is A. The next biggest region here is going to be B. This is going to be C, and this is going to be D. How can I also prove this? Look at the yield strength value, which is basically just given right here. Again, you can see it scales, and it's basically it's the same idea that's going on right here. So you could kind of confirm your answer both ways by either looking at the size of this cobalt creep region for this particular problem, since it's only grain size strengthening, or you can basically look at where that yield strength, because remember this line here, this line is basically your yield strength at different temperatures. Yep, that's it. So now we're just left with this one last question, fatigue. So don't get fatigued yet. One more, and we're finished with the practice exam 2. All right. Oops, excuse me. Thanks. Have a good one.